We're going to talk today about trees. Well, in particular, we're going to talk about binary trees, which is a specific type of tree, but I'll get to that too in a minute. Let me start with some definitions. Okay. So, what is a tree? This is a simple type of binary tree, and let's define a few things. A tree is made up of a bunch of nodes. That's, of course, all the circles here, and inside those nodes is a label, a data. It could be a number, it could be a string, it could be a boolean, it could be an object, it could be a list, it could be whatever we want to store there, right? It's the same thing as storing something into a list or any type of data structure. We get to choose what we store in those nodes. The nodes also are connected to each other through edges, but in a very special way. So there's an edge, and of course all the straight lines here are edges. The tree, as you can see here, has a parent-child relationship. So the nodes and edges can't be wired up arbitrarily. That's called a graph. So the parent is up top and the children are rendered below. So we have parent 1, child 2 and 3 connected by an edge. Child 3 has a child of its own. There are 6 right there with an edge. Child 2 has a child, which is 4 and 5, each connected by an edge. So we have a parent and a child, or you can say grandparent, parent, child, using a more genealogical, doesn't really matter. Okay. A couple of special nodes. The node at the very, very top is the root of the tree. Just think about the tree upside down, of course. And the leaves are along the bottom, and they are defined by those that have 0 children. Okay. So I said at the beginning we were going to talk about a special type of tree, a binary tree. What distinguishes a binary tree from a regular tree is that each node can have at most 2 children. So it can have 2 children, 1 child, or 0 children. So this node has 2 children. There they are. This node has 1 child. Perfectly fine. No child over here. This node has 2 children, and then all the leaves, by definition, don't have any children. Notice also there's sort of a recursive definition in this tree. Okay, and I'm going to mention this because we're going to do some recursion downstream here, which is this is a full tree, 3 levels here, 2 children, and then 3 leaves. But if we ignore the node 1, 3, and 6 and just look at this that's a little tree, perfectly fine, has a root up here and 2 children, and those don't have any. This is a tree also. There's the root up here, has 1 child, nothing left. In fact, just 6 is a tree. You can have a root with nothing underneath you. It's a sad tree, but it's a tree nonetheless. And so there's sort of this built-in recursive definition in trees. And again, the only distinction between binary trees and regular trees is I'm going to limit the number of children to be at most 2, 0, 1, or 2 children. Okay, one more definition I want to do, because I think we're going to use it down in a little bit, is we define the height of the nodes as essentially how many edges away from the root are you of the entire tree. So the root is at height 0. The direct children of the root are at height 1. The children of the root are at height 2. And if these children had children, well, then they would be at height 3, and so on and so forth. So we can keep adding levels and levels of the tree. You can see, by the way, the tree gets fuller and fuller and fuller. You can see, in fact, let's just do it now because we're going to do it eventually. This has 1 node. This has 2 nodes. Let's say that this was a full binary tree. So this would have 4 children. I doubled. What happened if the 4 children have children? They have 8. What happens if 8 children have children? 16. On every level, I am doubling the number of children. So that tree starts to get very, very full as we go down. But the height is, of course, only increasing by 1. There's sort of this interesting relationship there that I'm increasing the height by 1, but I'm doubling every time the number of nodes from the previous one. And we'll see why that turns out to be really interesting on the very, very last slide of this segment. All right, so let's build a tree. We just started talking about objects and classes, so that's how we're going to build it. Although you don't have to do it this way, but since we're doing it anyway, let's just go ahead and do it. So I'm going to build a class node. Now, right out of the gate, notice something. This is not a class tree. It's a class node. What I'm going to do is just build the ability to represent a single node with some data and a left and right child. Well, what's the left and right child? It's another node. So there again is that recursive definition. So I'm going to define a node. It has a single constructor. There's the underscore, underscore, init, underscore, underscore. Self, of course, is the address of the object that is going to be created for you of type class. I'm going to pass into this constructor some data. What is that data? Well, that's just going to be what I store in the node. So I've called it label here and data passed in, a little inconsistency there. Each node has what is it storing for yourself. That is the label or the data. It also has edges to 0, 1, or 2 children. So there's going to be a left child and a right child. By default, I will set those to none, which means there are no children. But as I begin to build up a tree, the root will have 2 children. What will these be? These will just be nodes of this type. There it is again, that recursive definition. Well, what will be stored in a node? Well, some data and then 2 more children. And so we can build up just by having a single node that points to 2 other nodes, and those nodes point to more nodes, and those nodes point to more. We have a tree. Okay, good. So that's all you need to represent a tree. There's a single class called node. Store some data into the data here. Store, and eventually we'll start wiring this up. Store the left and right, and we have a tree. Now we want to be eventually do things with the tree. We'll get to that in a little bit. All right, so let's build a tree. We actually have everything we need at this point to build it. So I'm going to define the variable root, because that's the root of the tree, to be a node, and I'm going to pass in the value 1. So there's going to be the picture, and this is going to be the code that generates it. Now notice there's no children. Why? Because the left and the right for this node are none. So I just choose not to represent anything for those. There's nothing there. All right, let's make a left child. All right, so I want to set the root's left child to be the node 2. All right, root.left. So what am I doing here? What is root? Root is an object of type node. I know that because I've called the constructor for node. Root has a label, that's the 1. It has a left child and a right child. And I'm going to set the left child, there it is right there, to be a new node. Notice now I'm calling the constructor again with 2 in the data. There it is right there. 2 doesn't have a left and the right child for the same reason 1 didn't have one in the beginning. And I'm going to set the root's right child to be another node with 3, and there it is right there. So I've now constructed a tree. And notice that in each case, I'm simply calling the node constructor as I promised, and I'm simply just wiring up what root points to. Okay. So now let's create another set of child. So what is this? So this is the root. This is root.left, that line right there, line number 2. Now I want to set the left child to be 4, and the left child's right child to be 5. So root, that's the top. Dot left, that's 2. Dot left is going to be equal to a node with 4 in it. And root dot left dot right is going to be a node with 5 in it. Now it's a little tedious the way we're having to build this. I have to keep traversing the tree, and if I had a really big tree, this would be incredibly annoying. We'll deal with that downstream. But for now, I just want you to get the concept here. And let's go ahead and just give 3 child also. So what is this? It's the root dot right dot left is equal to a node with 6 in it. So look at something sort of amazing here. All I have is this 5 lines of code here. I didn't really do anything other than just say every object has 3 things in it. Some data that you store and essentially two other things, right? In these case, I'm not forcing it here, but by the way I've constructed here, those are of course additional nodes. And now I have a tree. And what do I mean that I have a tree? Well, I could traverse the tree. If I started at root and I asked what is your left child, well, it would tell me 2. And if I asked, well, what is 2's right child, it would tell me 5. So this thing, just that one variable, sort of stores everything because it's been built up, right? I built up these connections between everything by virtue of simply building more and more objects. Okay, so it's really sort of surprisingly simple and elegant. All right, now, what do we do with trees? Well, there's a lot of things you can do with trees. We're not going to talk about all of them, but I'm going to talk about a few of them. And one of the standard things you might want to do once you put data in the tree is traverse the tree. Tell me something about what is being stored in the tree. And, unlike a list, with a list there's sort of basically 2 ways to traverse a list. Forward to back, forward to the end, end to the forward, right? So this way, this way. Trees obviously have a different structure, right? You don't just go from top to bottom. What does that mean? It's, well, here, okay, do I go to 2 or do I go to 3? And at the next level, so we have to think a little bit more about the traversal. I'm going to talk about 3 types of traversal. They're called pre-order, in-order, and post-order. You'll sometimes hear referred to as prefix, infix, and postfix. And you may have actually heard of those expressions before in the form of arithmetic operations. If you have, that's great. We're going to be talking about that in a little bit. So let's first talk about the first type of traversal. I'm going to just describe how it works, and then we're going to actually implement it. And we're going to implement it because it's going to show some really nice, cool recursion. Here's my tree. Height 0, height 1, height 2. The root has 2 children. This child has 2 children. This child has 1 child. Same one that we've been working with before. The pre-ordered traversal says to do the following. to print the root of the tree, the label at the root of the tree, and then print the entire left subtree, and then print the entire right subtree. Well, how do I print the left subtree? Same thing. Print the root, print the left subtree, print the right subtree. So there you can see the recursion. Okay, so let's go ahead and do that now. All right, so we're going to print the root. That is, of course, the 1. So I'll have the pre-order output here. Now my job is to do two things. Print the entire left subtree and then the entire right subtree. Okay, how do I do the left subtree? Let's just go back to the pre-order. Print the root and then the left subtree and the right subtree. And when I'm finally done with this whole left side here, I'll worry about the right-hand side. All right, so now the root 1, 3, and 6 are not my problem. My whole world is this little tree. And here it is again, that sort of recursive definition. Because I'm sort of doing a whole new pre-order traversal, root, left, right. All right, so we're going to print 2. Good. Now we're going to print the left subtree. That's 4. Now I have to print everything below this. Oh, there's nothing to be done there. There is no left and right, so I'm done. Now where do I go? Well, where was I a second ago? I was at that node right there. And my promise was to print this, the left, and the right. Okay, so let's go ahead and print the right subtree. That's the 5. Now, where was I? Okay, now we've got to remember, of course the recursion remembers for us, was that we printed the root. That's the 1 right there. We printed the left subtree. That was 2, 4, 5. Now we're done. There are no more subchildren here. Now we jump over to the right subtree. Good. What do we do? All over again. Print the root, the left, and the right. So we got 3, and then we've got 6, and then of course there is no right subtree, and now we're finally done. We did the root, we did the left subtree, we did the right subtree. Okay, good. Let's look at the code for this. Okay, so here's the Python code right here. It is a member function of the class node. So I've got a self right there. I'm not going to show you all the code because it's starting to get long, and I'm just going to show you the individual functions. So I have a traverse preorder self. It takes a node as input. We're going to pass it the root, of course, and it's going to do a preorder. But notice, I could have done this for any node. I can do a traversal of this subtree because it's the same thing. Root, left, right. But if I do a preorder on the root of the entire tree, well, then I traverse the entire tree. If I give it a node, an internal node, a child, a grandchild, well, then I just traverse that subtree. Perfectly fine. So what do I want to do? Well, the first thing we want to do is print the data stored at that node. So print self.label. Remember that label is the name of the data field being stored in the node. And I've just got this end equals space just so that there's no carriage return at the end. And so it just prints something out in one line. Now, okay, what do I want to do now? So I've done doing that. And now I want to print the entire left subtree, and I want to print the entire right subtree. Well, how do I print the left subtree? Well, I just have to do a preorder traversal. Well, how do I do that? Well, that's what this function is doing. So there's that magic, that leap over the cliff when you do recursion. We have a function that does a preorder traversal. And I just told you that doing a preorder traversal on that subtree or that entire tree, it's all the same thing. So if there is a left node, so if self.left, which means it's not equal to none, well, then just call the preorder traversal on the left subchild. Okay, how do we do that? What is self? It is the root of the tree. That's what we initially called it with. It has a left child. What is that? A node. If it's a node, it's of type object. And if it's a type object, I can call that member function. So self.left.traverse preorder, and now it's going to do this entire subtree rather. All right, and after that's done, what do I want to do? I want to do the whole right tree. Okay, good. So print the root, do the left subtree, that's this. Now, if the right child is not none, that means there is a right child, we'll then call the root's right child traverse preorder, and then we'll preorder just that. So there's that promise. Notice there's that recursion. This is easy. We do it, we're done. Now we're going to go off and do the entire left subtree for the root. And when that's done, we have to come back and do this, which is this side over here. Okay? Let's just do one step of the iteration here. So if I call self.left.traverse preorder, what's going to happen is that's now going to be self. That's the new object of type node. And what am I going to do? I'm going to print this guy. That's good. I'm going to print 2. Remember the preorder traversal was 1, 2. And then I'm going to print preorder traversal on 4, and then come back and do 5 when you're done. So there it is. 1, 2, 4, 5. When that whole subtree is done, then the left call for the root is done, and now I have to come back and do the right, which of course prints that, the left child, nothing on the right. Okay, so there's a nice little recursive function for traversing a tree in pre-order, which is root, left, right. Good. Notice that it's sort of inherently recursive. It would be hard to imagine how you could do this any other way. Now, another type of order. Remember I said there's pre-order, in-order, or post-order, or also infix, prefix, and postfix. So the in-order is just a different ordering, and of course post-order is a different ordering too. So here in order, we're going to traverse the left subtree, followed by the root, followed by the right subtree. All right, so let's see what that means. So I'm here, so I have to print the entire left subtree, and then you can print the root, and then print the entire right subtree. Okay, how do I print the left subtree? Well, nope, I don't do that. I do the whole left subtree, and then me, and then 5. Okay, that's done, and then I do 1, and then I do the left subtree, the root, and then the right subtree. So now, the code is just a matter of now of just reordering everything. So I said to do a in-order traversal, I print the left subtree. So if the left subtree is not empty, well then just call traverse in order on the left subtree. Good. When you're done with that, when that whole recursion finishes, please print the root. That's going to be 1. There's the print statement right there. And then when that's done, go ahead and print the right subtree. So the logic is exactly the same here. What have I done? I've just moved the print from here, the first line, to the next line. And that simply changes the order that I do everything in. Okay, so what's the order? Let's just play through it. So please, in order, traverse this tree. Okay, we're going to do the left subtree, followed by the root, followed by the right subtree. Okay, left subtree. Good. I'll come back to all of this later on. Okay, now how do I do this? Start all over again. All right, left subtree. There's my 4. Root, there's my 2. And right subtree, there's my 5. Okay, that whole left subtree of the root is now done. So now we go back to the root. Print the 1. There it is. Now we got to do the whole right subtree. All right, how do we do the right subtree? We do the left. That's 6. We do the root, that's 3. We do the right, there's no right, we're done. So 4, 2, 5, 1, 6, 3. Okay. By the way, notice that both in order and pre-order and not surprising post order, they print all the elements of the tree. It's just sort of the order in which we are doing them, hence the term in order. Okay. All right, so, in order seems weird. Like, why would you favor the left subtree over the root? I mean, the pre-order sort of made sense. You do the right, and then you got to decide left or right. So fine, do left versus right. So that seems like a logical thing. Why would you do this? Why would you favor the left subtree and then do the root and then do that? So it turns out there's a really interesting relationship between an in-order traversal of a binary tree and simple arithmetic expressions. So look at the tree that I've built here. It's a little bit different than the other one. First of all, it's a little bit bigger. It has a height of 0, 1, 2, 3. Still a binary tree. Everybody has 2 children. These are a little wonky because I couldn't quite fit all the nodes in here, so don't worry about the fact that they're not quite the same angle as the other ones. And now, but what I've stored in the nodes are a little bit different. So there's a multiplication sign, a plus sign, a 5, a multiplication sign, an addition and multiplication, and then a bunch of numbers in the leaves here. So let's go ahead and do an in-order traversal of this tree. Just a good exercise, and let's see what happens. Okay, so how do I do an in-order traversal? I sort of gave it away right there, sorry about that. So I do the whole left subtree, followed by the root, followed by the right subtree. Okay, I'll come back to that later. All right, so now this is my world. Do the left subtree, followed by the root, followed by the right subtree. Okay, I'll get back to that later. All right, here's finally, I think we're getting there. Left subtree, 3, root, right subtree. So 3 plus 4, that's right there. All right, I finished this left subtree. I got to remember a little bit where we were. I have another plus sign right there. That's the root. That's that plus sign right there. And now I have to do the right subtree. The left, root, and right. 4 times 2, that's that right there. Now, the whole left subtree is done. I'm going to do the root. That's the multiplication sign right there. And then I've got a 5, which is the right subtree, and of course, no children. What have I done? I have a simple arithmetic expression. So these binary trees, where you have operators and numbers mixed in, when you do an in-order traversal, can represent simple arithmetic operations. That's sort of cool and sort of nice, sort of intuitive way to do things. I don't like that there weren't parentheses around that, so I didn't put the code here because it got too long. But I could have adapted this code that said whenever you start a left subtree that is not a leaf, print an opening parenthesis. And whenever you finish a right subtree that is not a leaf, well then put a closing, and then you can get the in order to actually give you the parentheses that you want. So it's 3 plus 4 plus 4 times 2 times 5, right? So we get the sort of the ordering right. I've always found this really annoying about in orders. You have to worry about these parentheses. So one of the cool things about the post order, this is our last traversal, is it can disambiguate a little bit, and it's going to allow us to actually build trees a little bit more efficiently. So let's go ahead and look at this. So what is post order? Same game. So what did we first have? We had pre-order, which was root, left, right. We had in order, which was left, root, right, and post order is left, right, root. Okay, good. So the root just goes last. All right, so let's first look at the code. Sure, this is exactly what I expected. It's essentially the same code. So before we had the print, this is pre-order, and then left, right. And then we did left, root, right, and now we're going to do left, right, print. Okay, so let's just go ahead and do the traversal and see what happens. All right, so there it is right there. Let's play it out here, though. All right, so what do I want to do? I want to do left, right, and then the root. All right, so here I am. I'm going to do the whole left subtree, then I'm going to do the right subtree, and then I'm going to do that. That should be last. Oh yeah, there it is. Good. Now I'm going to do this one. It's going to be the left, the right, and then the plus sign. All right, what's this? Left, right, root. 3, 4 plus. Okay, now before I do this, I got to do the whole right subtree. So that's going to be 4, 2 times. There it is right there. And then I finally get the plus. Whole left subtree is done. Do the whole right subtree. Phew, there's only one node. Good, that's a 5. And then we do that. So this is called a postfix or post order traversal of the tree. Again, all the information is there, it's just the order in which it's not there. And the reason I like this is because it disambiguates and doesn't require parentheses to get the ordering of arithmetic expressions right. And it's going to turn out that it's going to help us build trees a little bit more efficiently. So remember that the way I built this tree was effectively just wiring everything up. So I started with a root and I put a multiplication sign there. I set the left child and the right child to be plus and 5. That's that right there. And then I set the left and the left and the right of the left child to be, etc., etc. And you can see that this tree, this code here builds this. And you can see that it's getting a little tedious. Even at height 3 here, I've got to go root, left, right, right. And now it's getting longer and longer and longer. And if I want to build any reasonable sized tree, it's starting to get a little tedious. Now, I could have fixed that by when I created the left, given it a different name, and then I could have said roots left dot left, but then I got to create all these variables too. So this is a little cumbersome, and it would be nice to be able to build a tree without having to enumerate left, right, left, right, left, right. And let's see how we can do that. And it's going to turn out, I don't think it surprises you because I sort of gave it away, is that the post order allows us to do that relatively easily. By the way, you can do this within order too. I just like the post order because it's really clean. The code is really clean. All right, so let's see what we have here. So this is construct a binary tree from a postfix expression. So here's my postfix expression. That's the one we just did, 3, 4, minus. I changed the plus sign to a minus sign because I wanted to show you right there. I didn't want an ambiguity between the two plus signs. Okay, so I just made a small change there. Okay, so what we're going to do is take a postfix expression, arithmetic expression, and we're going to build the tree without having to wire everything up together, and that's what this little code does. So we'll go through this together in a minute, but let's see what we have here. So we have something I'm calling a stack. It's just a list. Stack is a special type of list, the way I add and delete from it. I'll talk about that in a second. I've got a for loop here that's going to go through each character in the postfix string. So char here will take on each character in the string, and then what am I going to do? Okay, so I've got a conditional here that's going to check to see if it's an operator. I haven't given you this is operator function. It's just a function that returns true if the character it's looking at is plus, minus, times, divide, exponentiation. So it's the Boolean function that does a simple check on the character. So if it's an operator, I'm going to do something. And if it's not an operator, well, I'm going to do a little bit more. And then at the end, I'm going to return something. Okay, let's walk through and see what it does and make sure we understand it. Okay, so let's see, I got a bunch of moving parts here. So here's the postfix expression I'm going to pass into this function to build the tree. So its job is to build the tree that I'm going to show you over here. This stack here is where all the information is being stored, so I'm going to show you the values down here. So let me just say a word about a stack. A stack is what is called a FIFO, first in, first out. Okay? So what that means is that the first thing that shows up that is added to the stack is, sorry, it's a LIFO. Sorry, last in, first out. It's a LIFO. So the last thing that is added to the stack is the first thing out. So think about it as a stack of dishes. I put a stack of dishes on the table. The last one that I put on top, it's the first one you're going to take out. Unless you're weird and grab the bottom plate, you're going to take the one. So it's called last in. Plate that came on top is the first one out. The Q is the FIFO, the first in, first out. Okay, we'll talk about that later on in the class or in 61B. All right, so I'm going to, it's just a list, by the way. I'm not doing anything special here, but the way I add and delete from it is going to be in the definition of a last in, first out. So I'm going to append to the stack. That puts it at the end of the list. And I'm going to delete from the end of the list using this pop function, which says to take the last element in the list and remove it. So since I'm always going to add to the last part of this list, I'm always going to take away from the last part of the list. Okay, now let's see what that whole list is doing for us. All right, so first in, we're going to define stack to be the empty list. For each char in postfix, so it's going to be 3, 4, minus 4, 2, etc., etc. I'm going to, that's just one of my debugging lines of code, so you can go ahead and ignore that. So if not is operator the character. So if 3 is not an operator, it is not. Here's what I'm going to do. I'm going to call the node constructor and put the character in there. There it is right there. I've got a node, left and right are empty. And I'm going to append the 3, that's I'm going to append the node with the 3 in it into the list. Now notice I put a 3 in there, but notice what I actually appended is the object. Yeah, so don't think about that as the number 3. It is the node 3. I should actually put a little circle around it, but that was a little hard to do on the slide. Okay, so now I've got a tree with one node in it, and I've got that node in this stack list. Okay, so I don't obviously execute the else clause, so we go back up. The new character is now 4. Okay, it's not an operator, so what do? I create a new node, 4. Nothing's been wired up. I just have these 2 nodes hanging out there, and I stick that node in the list. Now, because those nodes are in the list, I haven't lost them. I mean, I haven't wired anything up yet. And by the way, notice that I'm wiring from the bottom up. That's because of the postfix notation. What does postfix do? Print the left, the right, and then the root. So the leaves are sort of in the beginning, which seems like it would be hard to construct the list. You'd think you'd want to start with the root and then hook up the child, but now you're going to see why this is relatively straightforward. So now my stack, my list, has 2 elements in it. The 4th was the last one in. The 3rd one was the one previous to that. Okay, next character is the minus sign. All right, it is an operator, so now we come into this else clause. And what does the else clause do? It says, create a node with the new character. That's minus. So there, I've created that node. Pop the stack, take the last element off, that's the 4, and make that the right child of the node you just created. T.right is equal to whatever you popped off the stack. That's the node 4. T.left is equal to pop the stack again and make that the left child. And then put this new node back onto the stack. There it is right there. So what have I done? I found an operator and I said, this must be an operator that has 2 children. What are the 2 children? Well, let's think about the postfix order. Think about just that one little tree, minus 3, 4. Well, what's the order? Left, right, minus. So if I read from left to right, I get the left child, I get the right child, and then I get the root. And since this is recursive, that's going to be true throughout the whole tree, and that's why this is so easy to construct. So we're going to just do this over and over again now, and you'll see how nice this becomes. So now I have this little tiny subtree right here, which is that bottom part of the list. Okay, good. Let's keep going. I'm going to come back up. I've got the 4. I'm going to do this in 2 steps, by the way, just to save a little bit of time. So I'm going to get the 4 and I'm going to get the 2. I create 2 nodes for them, 4 and 2, and I put them onto the stack in that order, 4 and then 2. So 2 is the last one for the. Notice, by the way, the minus 1 is still there. It hasn't gone anywhere. So that little subtree is still hanging out there. All right, let's go ahead and grab the next operator, which of course is the multiplication sign. That is an operator. Same thing. Create a new node with the multiplication operator. Set the right to be pop the stack, that's 2. Set the left to be pop the stack, that's 4. And then please put that multiplication onto the stack. So notice what I have here. I have these 2 little trees, the left tree and the right tree. And what am I going to get next? It's going to be the parent of those things. All right, let's go ahead and see what happens now. All right, so we get the next command, the next character. What is it? It's a plus sign. Okay, well, if it's a plus sign, there must be two things in the stack. There they are right there. So go ahead and create a new node with the plus. Pop the stack, get the right one, pop the stack, get the left one, and put that plus back onto the stack. Okay, good. So now we have that entire left subtree, and now you can see what the pattern is. So the next character is 5. I'm going to create a node for that. There it is right there. I'm going to put it onto the stack. The plus is still there. Left child, right child. I only have one thing left. That's, of course, the operator. I create a node, wire up, pop them, push the multiplication onto there, and then at the very end, I'm going to pop that, and we are off to the races. So notice that because of that very beautiful recursive definition of a tree, and because of that very elegant post order, which is not intuitive for you and me to look at, but because we did left, right, and then root, as I read this way, I know exactly the order that I have to wire everything up to. And notice, by the way, this only works when you have, of course, a binary tree, because we know that it can't be any more than 2 leaves. Okay, so I want to just spend a few minutes. I'm not going to talk a lot about this, but there's something really beautiful about binary trees, a very special type of binary tree called the binary search tree. You will eventually learn about this. Don't worry about it right now, but I just want to point out a few things. The binary search tree has the following property. It is a binary tree. This is a full one of height 0, 1, 2. And it has an interesting property about how I put the data into the tree. I have a root value. Every single value in the left subtree of that root is less than this value. And every value in the right subtree is greater than that value. So 7, 9, 10, greater than 6. 1, 4, 5, greater than 6. And that is a recursive definition. So if I come into this subtree, everything in the left subtree is less, everything in the right subtree is greater. If I come to this subtree, less, greater, and so on and so forth and so on. So it's a recursive definition for every node. Everything in the left is less, everything in the right is greater. And let's not worry about if they're equal right now. Let's say that these are distinct values. Now, how did I build this? Well, let's not worry about that right now. But why is this interesting? Well, let's imagine you're trying to find an element in a set of numbers. Yeah? And imagine I just gave you a list of numbers. Let's say I gave you 1,000,000 numbers and said, go tell me if this number's in the list. Well, you sort of got to start at the left and go through the list and go to the end and look for it. I mean, there's really nothing you can do. It's not in any order. But if it's sorted in this order, well, it's not really sorted, but if it's stored in this order, where everything is less and everything is greater, let's say I'm looking for the number 5. And I come up to the root here and I say, so what could I do? I could just traverse the whole tree, do an in-order, pre-order, or post-order, traverse the whole tree, and simply look for the number. That'd be a perfectly fine thing to do, but it'd be sort of dumb. Why? Well, if I'm looking for 5, what do I know? This whole right subtree can't be there. It can't be in there. So I really only have to worry about this subtree. Okay, so I come down to here. Now I'm looking for 5. Well, it can't be in the left subtree because it's greater than this, so I only have to look in the right subtree. So every time I make a branch, I lop off half the problem. Like half the tree just goes away. And then I lop off another half and another half and another half, and I have this very, very efficient way of searching for an element because the data is stored in this special way. Now, how did the data get stored there? How do I know the tree will be nice and balanced and pretty like this? Lots of really interesting questions. We're not going to talk about that here. I just wanted to give a little hint that these trees have really interesting applications downstreams that you'll be continuing to learn about. Okay, so binary trees, they are storing relationships between data and other data stored in these nodes. Super easy to build. We build a constructor with 4 lines of code. And then I showed you the traversals, the pre-order, the post-order, and the in-order, recursive definitions. And then I showed you that the post-order in particular was very nice because we could actually construct a tree from just an expression very nicely because of the very disciplined order. And then I added that one little thing, which is a stack, which is basically a list where you add to the end of the list and you take away from the end of the list. It's called last in, first out. And I just needed that to do the post-order construction of a binary tree. All right, that's it for now. I hope that was helpful, and we'll see you next time.